Hello everyone. Now in previous video also we have seen some examples on properties of integers. So here also let us see some more examples. So the first example in today's video, suppose if A divides B and C divides D, then show that AC divides BD. So solution, given that A divides B, so by definition of divisibility, there exists some integer k1 belongs to integer k1 such that what B is equal to A k1. B is some multiple of A, and call it as equation number 1 suppose, and C divides D, so that also gives there exists some integer k2 such that D is equal to C into k2. Call it as equation number 2. Now let us take a product of equation 1 and 2. Multiply 1 and 2. Multiplying 1 and 2, we get left hand side will be B into D and the right hand side is A k1 into C k2. So it will be AC into k1 k2. That is equal to AC into k, where k is what? K1 into k2. Now k1 k2 are integers, so their product is also one of the integers. So k belongs to Z. Now B into D can be written as some multiple of A into C. So this says by definition of divisibility AC divides BD. This is our required one. Now the next example is that evaluate the GCD of n plus 1 and GCD of n plus 1 and also LCM of n plus 1 for any positive integer n. So solution for this, now let the GCD of n and n plus 1 is suppose G. So by the definition of GCD, this G divides n and G also divides n plus 1. G divides n and G also divides n plus 1. So as G divides n, so this says there exists some integer such that n is equal to what? G into that integer. Again, and G divides n plus 1, so this says there exists some integer such that n plus 1 is equal to G into that integer. Now n plus 1, let us take this equation, n plus 1 is equal to G into k2. So let me put the value of n from equation, let us say 1. Now it will be 2 implies this. Now this is G k1 plus 1 is equal to G k2 from 1 we get this, fine. Now here we get 1 is equal to G k2 minus G k1. So that is same as G into k2 minus k1. That is same as G into k. 1 is equal to G into k. So this says G divides 1. So G divides 1. So one of the property of divisibility, it says G is less equal 1. But G is what? A GCD of n and n plus 1. So it won't be less than 1. So it must be equal to 1. So here this says G is either less than 1 or G is equal to 1. Okay. So this implies G is equal to 1 as G is what? G is GCD. G is a GCD. Now, hence we get the GCD for n and n plus 1 is G, that is what? 1. So, GCD of n and n plus 1 is what? 1. And means the GCD of two consecutive integers is what? 1. Now, we have to determine LCM. So, LCM, to determine LCM, there is a relation between them. What does that relation? The product of these integers upon their GCD. That is the result for LCM. So, product of them is what? N square plus n. And what is GCD here? 1. So, the LCM is what? N square plus n. Therefore, the LCM for two consecutive integers for any integer n is what? N square plus n. Is this answer? Fine. This is the solution of this example. Now, let me take the next example. The next example is that find the values of, next example, find the values of, GCD of A and B and LCM of A and B. If A and B be any positive integers, such that A divides B. A is a divisor of B. That time what are the GCD and what are the LCM of A and B? That one we have to determine. So solution here, again let me assume that the GCD of A and B is G. Suppose GCD of A and B is G. So by definition of GCD, again G divides A and G also divides B. Now here we can use the linear combination theorem or the existence theorem also. If the GCD of A and B is G, therefore there exists some integers xy such that A into x plus B into y is equal to what? G. This is equivalent to G. Call it as equation number 1. Also given that A divides B. So this says there exists some integer such that B is equal to AK. Therefore, 1 implies AX plus AK into Y is equal to what? G. So, here take A common, we get X plus KY. X plus KY equal to what? G. So, this says A divides G. By definition of divisibility, we get A divides G. So, let it be equation number 2. As G is the GCD of A and B, so this says G divides A. Call it as equation number 3. Now, from 2 and 3, what we get? We get A divides G, G divides A, means what? A is equal to plus minus G, but G is in GCD, and here given that A and B are positive integers. Either we get A is equal to plus minus G or G is equal to plus minus A. But as they are positive, so we get A is equal to G. So from 2 2 and 3 we get A is equal to G. Now A is equal to G means what? But what is G? We have assumed G is the GCD of A and B. Therefore, the GCD of A and B is what? A, as A divides B. As A divides B. This is given to us. Fine. Now, let us determine LCM. Now, LCM is what? It will be A into B upon the GCD of AB. So, it will be A into B upon A. So, we get it is what? B. As A is positive, so it cancel. We get the LCM is what? B. The LCM will be what? B. Okay. So, as A divides B. This is the given thing. So, if A and B are positive integers with A is divisor of B, then the GCD is A and the LCM is B. Now, next example is that, show that if X and Y are odd integers, then X square plus Y square is even, but not divisible by 4. So let us try to find, or let us try to show this. So what is given? X and Y are odd integers. Now you know odd integer can be written as either 2k plus 1 or 2k minus 1. So let me assume X is equal to 2k1 minus 1 and Y is equal to 2k2 minus 1. Be any odd integers. Obviously here these k1, k2 are what? Another integers. Fine. Now let us assume what is x square plus y square. X square plus y square means what here? 2k1 minus 1 square plus 2k2 minus 1 square. So 2k1 minus 1 square, use a minus b whole square identity. So we get 4k1 square minus 4k1 plus 1 plus 4k2 square minus 4k2 plus 1. So that is same as 4k1 square minus plus 4k2 square minus 4k1 minus 4k2 plus 2. Now x square plus y square is what? 2 into 2k1 square plus 2k2 square plus minus 2k1 minus 2k2 plus 1. We can take 2 common from there. Now here this part belongs to Z. This is belongs to Z. K1, K2 are integers, so this whole one will belongs to Z. Let it be K, where K is equal to what? 2k1 square plus 2k2 square minus 2k1 minus 2k2 plus 1, and it belongs to Z. K, we are naming it as K. So we get x square plus y square is equal to what? 2 times K. So what does this say? This says 2 divides x square plus y square for K belongs to what? Z. For some K belongs to Z. Now we know that any even integer is always divisible by any even integer is always divisible by what? 2. So this says x square plus y square. If you look it carefully, this x square plus y square will be even, or this is odd integer, or the square of an odd integer is odd, this again square of an odd integer is odd, but their addition will become even. So x square plus y square is even. So x square plus y square is even, that's why 2 divides x square plus y square. Now suppose 4 divides x square plus y square. Our aim to show that x square plus y square is even, that one we have been shown, but not divisible by 4. Now on a contrary, we will assume 4 is x square plus y square is divisible by 4, or 4 is a divisor of x square plus y square. So if 4 is a divisor of x square plus y square, so there exists some integer such that x square plus y square is equal to what? 4 into that integer. Fine. Now, but we have x square plus y square as this part, 4k1 square plus 4k2 square minus 4k1 minus 4k2 plus 2, as x square and x and y are odd integers. Therefore, we get 4k3 equal to this 4k1 square plus 4k2 square minus 4k1 minus 4k2 plus 2. So this says, this gives 2 is equal to, let me take this 4k3 on this side, on another side, or let us keep this 2 on this side, let us take other terms on another side. So 4k3 minus 4k1 square minus 4k2 square plus 4k1 plus 4k2 is this. Now from this we can take 4 common. So 4 will be common. What does it give? k3 minus k1 square minus k2 square plus k1 plus k2. Now this is another integer, as all k1, k2, k3 are integers. So this can be written as 4 into k dash, where k dash is what? k3 minus k1 square minus k2 square plus k1 plus k2. This is what? An integer. This is an integer. So we get 2 is equal to 4k dash. 2 is equal to 4k dash. So what does it say? This says 4 divides 2, which is not possible, which is a contradiction, which is impossible. Which is impossible, because the divisors are either equal or less than that number. 4 cannot be divides 2. So here this is a contradiction. Why does this contradiction occur? Because we have assumed 4 divides x square plus y square. So what does this says? 4 doesn't divide x square plus y square. This is our answer, or this is a proof of this example. Now the next example is that, prove that, next example is that, prove that there are infinitely many pair of integers x and y satisfying the condition that the GCD of x and y is 5 and x plus y is equal to what? 100. Okay. Now the solution of this one, given that the GCD of x and y is what? 5. So this and x plus y is equal to what? 100. This is given to us. Now GCD of x and y is 5. So this implies 5 divides x and 5 divides y. Now 5 divides x means what? X is equal to 5 times some integer, and 5 divides y means y is equal to 5 times some integer. So for some k1 k2 belongs to what? Z. Fine. Now as x plus y is equal to what? 100. Therefore we get 5k1 plus 5k2 is equal to 100. So 5 into k1 plus k2 equal to 100. Therefore k1 plus k2 is what? 100 upon 5. So that will be what? 20. So addition of two integers is what? 20. This is possible for infinitely many integers. So here k1 is equal to 20 minus k2. Well, it is equation number 2. Let it be equation number 2. This is equation number 1, which we have been used here. Fine. Now here for various values of k2 we get k1. So we can say this shows that by choosing values of k2 we get values of k1. That is, there exist infinitely many values of k1 k2 satisfying equation 2. Therefore by choosing values of k1 k2 we get infinitely many values of x and y by equation 1. While k1 and k2 are infinitely many, so x and y are also infinitely many. Thus there are infinitely many values of x and y such that the GCD of x and y is 5 and addition of x and y is what? 100. Now on the contrary, there is another type of example. Let me take that one. Prove that there is no integer x and y satisfying. Another example is this opposite kind. Prove that there is no integer x and y satisfying the GCD of x and y is 3 and the addition of x and y is what? 100. Now solution of this one, just like previous one. Given that the GCD of x and y is what? 3 and addition of x and y is what? 100. Now as GCD of x and y is 3, so this says 3 divides x and 3 also divides y. So this says x is equal to 3k1 and y is equal to 3k2. For some k1 k2 belongs to z. Now x plus y is equal to what? 100. This is given, another condition. So let it be equation 1. Now x plus y is 100. Let us substitute the value of x here. 3k1 plus 3k2 equal to 100. So this says, this is from 1, we can say, from 1. Now this is 3 into k1 plus k2 equal to what? 100. So here we get k1 plus k2 is equal to 100 upon 3. Now, or from this, here we get 3 times k is equal to 100, where k is equal to what? K1 plus k2, and that belongs to what? Z. Now this says 3 divides 100, which is not possible, or which is a contradiction. Hence it is not possible. That there exists a pair of integers satisfying that the GCD of x and y is 3 and their addition is 100, satisfying these conditions. So here we will stop for today. In next video we will see some more examples. Thank you.